So all this is salt water, and the sodium chloride is just there to provide a conduit for the electricity to flow. The main focus is going to be the water. So I've got a power source hooked up, and I want to put this in here, and when you drop in these leads, you're going to see bubbles being formed, okay?
It's electrolysis.
Oh, it's electrolysis. Yay, for those of you that have taken AP chemistry, you kind of get an advantage on this lesson.
Perfect.
So here's the story. So what we're doing is that we're going to force electricity into there.
Stop filling up the balls.
To force the water to break apart. So basically what we're going to have is a decomposition of water into hydrogen and oxygen. Now, conveniently, that is not a spontaneous reaction where hydrogen spontaneously decomposes into hydrogen and oxygen, because if it did, we wouldn't be here having this discussion, because spontaneously the water inside your body and in the oceans would change into hydrogen and oxygen. Oxygen is fairly flammable, bad things are going to happen. It's like, hey, don't smoke near the ocean, you might cause an explosion. That would be a one-time mistake. Now, out of this, you also produce some byproducts. You produce hydronium ions, which are positively charged, and you produce hydroxides, which are negatively charged. That's the whole point of the story. Out of byproducts, you get hydronium ions and you get hydroxide ions. So, one way we can tell that that's happening is that we can use this stuff. It's called phenolphthalein. It's a universal indicator. So, if it's in the presence of the hydroxide ions, which are negatively charged, this turns magenta color, okay? So I'm going to put some of this in here, right? And we got this nice magenta, and I put this in here, and when that goes, you'll notice that one side of that is very much producing a magenta color. So what that means is that this black lead over here, don't worry about it's positive or negative, just remember that that's what's producing the negatively charged ions, which means the red side is producing the hydronium ions, which are Ace plus. So here's the point of the story. The red one is producing positively charged particles. The black one is producing negatively charged particles. Now, we haven't introduced the magnetic field yet, but we're going to. So I'm going to take this. Okay?
How's the first half?
And,
And electrolysis, what kind of magnetic witchcraft are you trying to?
oh,
So
yeah,
you know how like particle accelerators work? It's that.
pretty much, yeah. That's how. So
Yes,
I'm going to
Andrew,
do
we
this.
all know how particle accelerators work.
So now, I'm going to put a neodymium magnet underneath. Okay. Turn on the light, so it's a bit more dramatic. And then we're going to add a little bit of phenolphthalein, so we see what's going to happen. A little bit of a new off factor. So right now it's clear because water is neutral. So now I'm going to do the same thing. So you all saw what happened when I didn't have the magnet. It just kind of bubbled and it just kind of stayed there. But now if I do this same thing and I put a magnet underneath it, now when I do that, you'll get a swirling action going on. So stand up so you can see. You got to look down on top of that. So what you're seeing is that the particles are moving. Now, if I take that magnet out, nothing happened. It was stationary. So what that tells me is that these particles, and if I move them really, really close together, okay, or change that distance, that affects that rate. So what's happening is that these particles, you have like a north and south pole of this magnet. So if I don't have charged particles and it's just sitting up there on the water, nothing happens. You don't get the vortex. You only get the vortex created when you have charged particles. So one of the things necessary to create a deflection of particles is that you have to have charged particles. I am this close to just shutting up and just giving you the assignment. If you want to play with toys, find another room. God. So when this is happening, you've got these going in a particular direction. So positively charged particles interact in one way, negatively charged particles happen in another. Now, if I take this and flip the magnet over, and they do the same thing, you'll notice that they go in the opposite direction. Okay? So what that tells me is that if I switch the magnetic field, the direction of the magnetic field has something to do with how the particles move. Because if it was just a magnetic field that caused it, whether it was north or south, nothing would change. But because when I flipped it over and it went in the opposite direction, that tells me that the direction of that magnetic field is going to have something to do with the direction of the force that's acting on it. Now, how do you know a force is acting on the particles?
They're moving.
They're moving. Otherwise, they're just going to remain stationary. So what that tells me is that, hey, F equals ma. There's got to be a force. So without that force, I don't get an acceleration. Got it? Good. Back we go.